so we're going to make equations with lines and align to a vector. So what I did is I went from the center of the universe, 0, 0, went to a point on the line, and that vector from the center of the universe to the point on the line we call A. This is x1, y1. Then I go in direction B, which is this way, and B is also a vector, A, B, and then we can go as many steps as we want, lambda. So this is what I call the point on the line. This is the direction on the line, and then this is the number of steps. All that is to get this vector, which is the result of points on line. And this is really super helpful because if you want to know where a vehicle is, this lambda becomes a variable which we call time, and in time we can place that wherever we want on the line. And we can look at intersections, see if they crash or not, things like that. All right, so did he talk about the other ways of getting that? Okay, so I'm going to stop the video here. We'll continue with intersection of a line in just a moment. Here are a couple of quick examples. We're going to take a point and a vector, and then we'll take 2 points, and we're going to create all these different forms. So let's do the vector form, the easy one. Start with xy, then we have a point, then we have lambda, and then we have a direction. So the point here is 5, negative 6. The vector direction is 5, negative 3. So this is my point, and this is my direction. Ooh, that's pretty smooth. Now for the parametric, I'm going to the dark side here, and I'm going to highlight this one and this one. So parametric is just x equal to 5 plus 5 lambda, and y is equal to negative 6 minus 3 lambda. That's the parametric. How many of you feel pretty good about those 2 forms? Okay, good. Now the Cartesian is the most helpful because you can actually graph it, and it doesn't have lambda in it at all. And the way you deal with this is you would go x minus 5 equals 5 lambda, so x minus 5 over 5 is lambda. Do the same here, y plus 6 equal negative 3 lambda, and so y plus 6 over negative 3 is equal to lambda. Just doing the algebra, solving for lambda. Is it true, Jackson, over here, that 3 is equal to 3? Is that true?
Yes.
Okay. I'm going to go out on a limb here. Is lambda equal to lambda? Yeah, it's just the same thing, right? So I'm going to take that lambda, x minus 5 over 5, and set it equal to the other lambda, y plus 6 over negative 3. This is what we call Cartesian form. Done. So there you go. There you have it, number 1. Let's go for the second one. This is has what I call the key to the whole chapter in it. You have a point we'll call A, negative 2, 7, and a point B we'll call 3, 9. For vector form, we still do the xy. We're going to put in a point, and which is your favorite point, A or B? Good, 3, 9. Either one will work. And then we go lambda direction. Now, to get the direction, we're going to do vector AB. So, Ella, which is the head here, A or B? B, yeah, no, it's a little confusing. The tail is here, the head is where, the head isn't the first, it's where the arrow is pointing to. So we do the head minus the tail to get the direction vector. So in this case, it's going to be 3 minus negative 2 and 9 minus 7. And that's going to be 5, 2. And guess what 5, 2 is? That's your direction of your vector. Yes?
Can you also just do it by finding like the change in y and the change in x of the, well, I guess that is what you're doing.
That's exactly what we're doing, yep. Now the question is, what if I would have done this backwards and gone b minus a? Well, if you would have had a negative 5 over negative 2, then all your lambdas would be the opposite, and it really wouldn't hurt anything. It would still work, but just do the A, B, get that direction. Now, once you know that, now we can do the parametric. X equal 3 plus 5 lambda, and y equal 9 plus 2 lambda. Then when you want to find Cartesian, no problem, x minus 3 equals 5 lambda, we're going to divide by 5. Y minus 9 equals 2 lambda, we're going to divide by 2, and those will be equal. So there is your parametric, your Cartesian, and your vector form. All three. And so here is a parametric equation. We're going to see if these collide or not. Instead of lambda, my step, it's going to be time, and we're describing x and y in time like that. Well, let's make the vector equation first. xy, what's the point? Good answer. But what's the point of this problem? Well, yeah. Well, what's the point from the center of the universe to this spot? 4, 5, yeah, good. And then we'll have lambda, except we'll have t this time. And what's the direction vector of this? 5, negative 2. So this is my vector equation. But something really interesting happened here. Now that it's representing distance, this xy is my distance. And what do you know in physics about adding things? Can you add speed plus distance? Can you add acceleration plus distance? What can you add to distance? Only distance. So it makes sense that xy is a distance. What's 4, 5? A distance. What does that make t times 5 negative 2 to be? What does this whole thing have to be? A distance. But since there's time times what is going to give you distance? Speed. All right. This thing here is the speed. And you can find it real easily by finding the magnitude of that vector. The magnitude of that vector is just going to be the square root of 5 squared plus negative 2 squared, which is the square root of 29 units per second or minute or whatever the time is. That kind of came out of nowhere, didn't it? Kind of neat though. I want to know if this object, if whatever this is, will hit a car at 19, negative 1 position. So what we'll do is we're going to change our xy into 19 and negative 1. This is a glimpse into what we're going to be doing tomorrow with real stuff and vectors. So x is 19, y is negative 1. 19 equals 4 plus 5t. What would t have to be to make this work? 3. T would be equal to 3. So it takes 3 seconds for the x's to align. 3 seconds for the x's to align. Now is the y early, late, or on time to collide? Let's see. Now we're going to go negative 1 equal 5 minus 2t, and we're going to subtract 5, give me negative 6. What's t going to be this time? Negative 6 over negative 2 is 3. So if the y's hit in 3 seconds and the x's hit in 3 seconds, what can we say? Will the car hit this? Yes, it'll hit. Sad, but it's true. And if we were in 3D, all you need is another variable, z, equal 3 plus 6t. Okay, so we're getting to the good stuff now. Well, let's try this. So we have a vector 2, 3, over 2, up 3, and let's see, in direction forward 2, up 1. So here's the line. going like that. This one is 5, 1, 2, 3, 4, 5, down 2, and we're going in the direction, let's see, forward 1, down 2, right? Forward 1, down 2, okay. And will these ever hit? No, but if my mu and lambda's steps were negative, do you think they could hit? Yeah, they could. They could. So we're going to see when that would be. You're going to use only an algebraic technique to find out when and where they're going to hit. So to do that, we need to convert these two into parametric forms. So let's do that with this. Whenever you see R, what do you change it to? Thank you. And then the point is here. So that's 2, 3. And then the direction vector is going to be 2, 1. You make this second one. For this second one, did you get x, y equal to 5, negative 2? And then we're going to use a different step value here, mu. We'll go instead of lambda. Did you know that this is the Greek letter mu? How many of you have not seen this before? Okay, here, let me show you. The way to remember it is this is the Greek letter mu. Oh, that's bad. That's really bad. That was your little diversion to art class. It was fine, but very short-lived. Okay, so mu will be 1, negative 2. I saw that in a journal somewhere. They thought it was funny. You didn't, but that's okay. So then what we'll do is once we get these two, now you're going to break these up. I'm going to shrink this first. Now what we're going to do is we're going to break these up into the parametrics. X equal to 2 plus 2 lambda, and y equal to 3 plus lambda. And then we're going to have x equal to 5 plus mu, and y equal to negative 2 minus 2 mu. Mu. So we want to find out where they intersect. Any ideas? Got a lot of variables here. We have 1, 2, 3, 4 variables. Any ideas? What about these two? What are those equal to? What's x equal to? X, is that true? Sure is. Since x is equal to x, you can say 2 plus 2 lambda will be equal to 5 plus mu. And I like to get this 5 over here. Negative 3 plus 2 lambda equal to mu. There you go. There's one. The second one is y equal to y, always true. So then we go 3 plus lambda will be equal to negative 2 minus 2 mu. I have to move this 2 over. 5 plus lambda equal negative 2 mu. Oh, that's great. Why is that great? Because we have two equations now and two unknowns. We can write these. Negative 3 plus 2 lambda equal mu, and 5 plus lambda equal negative 2 mu. Go ahead and take a moment and write that. And draw a line under it, because we're going to do an elimination that way. Please copy. Because you'll be doing this for sure on a test. We'll get an R, it'll be an R3-er. And we want to get rid of the mu's or rid of the lambdas. I'm going to multiply everything. Let's multiply the bottom by -2, -2, -2, -2. So this is going to give me -3 plus 2 lambda equals mu. And then on this other one, you're going to get -10 minus 2 lambda equal 4 mu. All right, so if we add these up, -3 and -10 is -13 plus 0 equals 5 mu. So it looks like mu is -13/5. It's okay. We love fractions, right? Oh, we don't. That's right. I keep forgetting. I knew we liked them or we didn't like them. I knew it was one of the two. All right, so if we know what mu is, now we can find intersection point. This is great. We can find the intersection point. X is 5 plus -13/5. Y is -2 minus 2 times -13/5. So that's going to be 25 minus 13 will be 12/5. And let's see, this will be -10 plus 26 will be 16/5. So the point of intersection will be 12/5, 16/5, and that is true. You could have found lambda and you would have gotten, last hour we solved for lambda and we got the same thing. So it's pretty cool. You can't go wrong with picking lambda or mu to eliminate. So going back, what we did is we changed these into vector form, then vector form into parametric. Parametric, we set the x's equal to each other to eliminate x, eliminate y, and then you had those two, and then you took those two and you eliminated mu or lambda. We eliminated lambda, found out mu, and then we plugged it into the mu formula so that we could get the intersection point. Now I can say, did you get the point?
Yes.
Yes, you did. Yay. Good. All right, go down to homework. Zip down to number 8A. I want you to see how far you can get in finding the intersection of these two lines, and part B as well. And then for those in the computer world, go ahead and work on that assignment. And these answers are worked out.